All right. Good evening, everybody. How are you doing? Hi, Yunlong from Singapore. All right. From Saudi, Mohammed. Welcome, welcome. All right, let's get started. It's 8:30 Singapore time. All right. Let me turn off the music. I hope you enjoy the music. All right. Yeah. We have Mr. Viresh here. Right. Yeah, Viresh. Okay. All right, let's get started. Thank you everybody for joining on time and earlier. I think we're going to have a very packed session today, right? So let's get started, right? Okay, give me 1 second. All right. Can confirm you can hear me clearly. You can see my screen. You can see our face. Yes, excellent, excellent. All right, okay. Uh, just as usual, I'm sharing about the few upcoming sharing session again. Uh, Actually, before this webinar, I just had a call with my friend Jonathan Ayala. Right, he based out of Germany. And we will have a discussion on what actually scale-up engineer does. Right. So I guess yeah, most of us are familiar with operating company, maybe designing a plant, but actually there is a process of scaling up from the lab pilot to actually plant, right? So Jonathan will talk about that on 20th June. I will also have a friend, Dr. Zuvan will talk about distillation column on 27th June, right? The registration link will be shared in this PDF, right? And also on the on the 2nd July, has been rescheduled to 25th July. I forgot to change because just 30 minutes ago. Uh, uh, Jonathan will talk about direct air capture technology, right? So we will talk about the trend in the industry. I think that will be exciting. And 11th of July, I will present about the HYSYS dynamic simulation, right? giving you an overview of or getting started of HYSYS, right? So that's that. Disclaimer, the presenter speaking here, right? We are speaking out of our personal capacity. We're not representing our current or past employer, right? Our view, which we express in this technical sharing, is our own view based on our own industrial experience, right? Which may or may not be supported by our current employer or past employer, right? So just get that. All right, so I think I'm not going to introduce myself. Anyway, just a brief, really brief is I'm chemical engineering currently, working with Aspen software company, right? One of the solutions is Aspen Plus and HYSYS, and then a few others, right? I'm focusing on engineering solutions, right? So I've been working for 5 years with Aspen since 2019, right? So without a further ado, let me introduce the speaker today, right? Viresh, process engineering consultant. He has more than 35 years of experience of operating and designing a oil and gas facility. Right, he has worked with oil and natural gas corporations India, Zakum Development Abu Dhabi, Petronas Carigali Malaysia. Right, actually I met him in Petronas, Perunding Ranhir Woli, Malaysia, GSI Singapore, Parson Oman, Bechtel India, right? So he has a lot of experience, right? He provide consultancy to different contractors on revamping, designing, troubleshooting, optimizing studies, including fire survivability study, right, which we'll touch on tonight's session, right? He graduated chemical engineering from Harcourt Butler Technical University, Kanpur, India, right? Viresh, say hi. All right. Okay, just a little bit housekeeping. I think many of you has been joining the session, so you know where's the button for chat, where's the button for Q&A. But this is giving you, all right. The most left is for chat, right? You can put if it's a comment or etc. Hi, or you can put in the chat. But for questions, please do put it in the tab for the question and answer, right? That makes us easier to go through your questions, right? Okay, so we will also have a poll that's on the third one, and later we will also provide the slide deck of this presentation. Okay, all right. I don't wanna. Okay, uh, I'll go fast. Basically, the session will be two parts, right? So I will cover the first part, kind of giving a little bit overview of the blowdown, especially the technicality on the kind of the availability of tools in HYSYS, the different step you need to do, right? And the important part is the case part two, right? Which is Viresh will deliver um, is on the case studies, the different case studies using depressuring utility as well as the blowdown utility, right? So I'll turn off my video now, all right, to save the bandwidth, right, and to allow you to focus also on the content, right? All right, let's get started. All right, so the blowdown, right? uh Depreciations, right? So what is actually blowdown analysis is basically we want to rapidly reduce the pressure or depressurize the vessels, right, or equipment, right? When we actually do it this, right, typically okay, maybe first why we do do it do why do pressurize the system, right? So basically one is to move to evacuate, right, to the inventory hazardous material, right? Let's say your separator you contain of your hydrocarbon gas, your liquid, right? Most, and the second one also to reduce the stress of the vessels, right? The high pressure is actually is high stress to the to the vessel. With reducing the pressure, you get less stress to the vessels, right? Okay. And what's when we do the blowdown analysis, right? Basically, one of it we need to ensure that the vessels actually will not rupture due to fire or also due to cold temperature. So this is also part of the risk assessment, right? Okay. Uh, and before Aspentech actually acquired Blowdown from Imperial College. Before this, a lot of these calculations is done using tools called depressurization depressurization utility, right? Right? Which is also runs in dynamic, right? And when there is an issue, like for example, low metal temperature is accounted or encountered in that analysis, right? Then typically the engineering contractor will subcon the more detailed study, right? One of it to Imperial College, right? I think remember maybe another one is to Technic, right? So we do have that methodology or algorithm from Imperial College now incorporated in HYSYS. Right. So typically, what are the uh, what are the questions we want to answer, right? So depending where, let's say we are designing a system, right? So when we are designing a system, definitely we want to size the system, and one of it is to what is the size of the orifice, right? To allow that we will achieve or we will reduce the the pressure, right? Let's say based on the criteria, right? It could be half of the design pressure within 15 minutes, right? So what flow rate we need to pass through to that orifice, right? So what is the let's the peak mass flow rate which going need to pass through to that orifice, right? So this also will determine kind of size of the pipe in that system, right? It could also influencing the flare system on the main header and the downstream system, right? On the flare. Okay. And also typically we also will look into the temperatures, right? This will impact in terms of what materials should be selected, right? Of course, if we encounter low temperature, then probably we need to switch to a more appropriate like stainless steel temperature, right? Sorry, stainless steel material. Okay, just to cover a little bit of uh, the criteria for blowdown, right? So this is the acceptance and design criteria to depressure the exposed equipment such that the reduced internal pressures keeps the stress below the rupture stress until the acceptance criteria for the ruptures are reached, right? So basically, for the depressurizing rate, in case of the protecting vessels of exposed to fire, right, a vapor uh, depressurizing system should have adequate capacity to permit reductions of the vessel stress to a level which the stress rupture is not an immediate concern, right? And this is just I think also to perform a more specific calculations. This section A3546 provide a method that might be used for specific calculations involving pool fire as well as a jet fire. Right, so you can see in this diagram, I
Fauzi,
took this from.
excuse me,
Yep, go
Fauzi.
ahead. Sorry, Firesh. Yep,
Looks like the audience are unable to see the slides properly. There's a obstruction of our profiles to the slide. Can we hide our profiles?
profiles.
The one with
I
the
think
our window,
let me stop and be sharing if that helps. Just in case, right?
and people have requested about the recording also.
Yes, thank you. So the the recording will be provided to you, to your email, definitely, right? We will send that to your email, and also the handout we will post the handout towards the end of this. You can download as usual, right? Okay, let me share my screen again. Thanks, Viresh. Let me know if this looks better now. Okay.
Yes, people say
All
yes.
right.
Mm.
All right. Cool. Thank you for the confirmations. Yes. So you can see here, uh, basically, right? Let me enable my pointer. Okay. So, especially during fire, right? When during fire, when the vessel is exposed to fire, right? It contains first is probably is isolated, right? The hydrocarbon is inside. If we didn't remove the hydrocarbon, the pressure is still remains, right? With the additional heat input from the fire, the pressure will increase, right? It put more stress, right? So until, and the other thing also, with the increase of the temperature, also the strength of the vessel also reduce, right? So that's a kind of like the dual challenge we're facing right now, right? So one is reducing the same cost, causing reduce of the strength as well as increase of the kind of the load or the stress, right? So until that cross, right, then that means the vessel will rupture, right? And if we have not removed or we have not minimized the inventory, right, that will be catastrophic, right? So you can see also here in the second diagram, right? Yes, this is the vessels strength are reducing, but you can see there is a red line. The stress from the vessels is also reducing. Why? How this is achieved is basically we are removing or reducing the pressure from or removing the inventory which caused the pressure reduce in the vessels, right? By doing that, we can actually prolong that, right? And hopefully, even if it ruptures, right, the inventory is really kind of minimum uh, level, right? Okay, let me move, right? So this is actually a share from Viresh, right? So I think he highlighted that this is a very important references. These two, which he highlighted here, is very important references that we must read before we actually attempting to carry out the blowdown studies, right? Okay. All right. So let me go through this. Okay. So I want to share a little bit before we have the blowdown utility. We actually have the depreciation utility, right? So in that depreciation utility, if you have used it before, uh, we will calculate the total volume of the systems, right, including the piping as well as the vessels. And typically we do these calculations in Excel, and we come up with kind of a new equivalent vessel dimensions, right? So in essence, that we actually combine all that volume from pipings as well as the main vessels, right, into one single vessels with a new dimension which reflect the system volume, right? So by doing that, so, right, when if we actually run the calculation, the depressurization calculations and encounter low temperature, it is hard for us to actually determine, or it almost is impossible for us to determine which actually is it really the vessel or is it only certain piping, right? We can't know, right? Because it's everything is combined into one single volume or system, right? Okay, so if we make decision based on that, right, we have to change the whole system, let's say to stainless steel, then it will be a major cost impact to the project, right? Okay, so in the blowdown utility, right, in the blowdown utility, now basically we model all the system individually, right? So when you go through the blowdown utility, you will specify what how long is the inlet piping, right? The horizontal part, the vertical part, right? All the other lines, also the vapor outlet, the blowdown inlet line, the tailpipe, right? So all this is actually we define the system individually, the pipes, the vessels separately, right? So we are inputting the individual component, right? So when we have an issue or the calculation detected low temperatures, we can actually know exactly which part of the system actually exposed to the low temperature, right? Okay. Okay. So just to give also it the blowdown technology, which is incorporated in HYSYS, is acquired from Imperial College, has been validated, right, with over 400 projects, right? So it does help to minimize capex, right? Validate the wall temperature predictions to within 3 Kelvin, right? Eliminate uncertainty in analysis by using fully predictive, rigorous thermal package, right? Okay, this is a background. It's developed by Dr. Graham Saville, right, and Professor Stephen Richardson from Imperial College. Initially, Blowdown is offered as a consulting service by Imperial College, right? Before it acquired and incorporated into HYSYS. Okay, so it was trusted and the gold standard of the technology for depressurizations, right? And it has been validated against actual plant data for nearly 30 years, right? Uh, we have so you can predict the accurate temperature within plus minus 3 degrees Celsius, right? Dynamically simulates the hydrocarbon flow from multiple depressuring vessels and other equipment, and also is fully predictive model, right? So uh, maybe many will ask, what's the kind of the difference between the legacy depressuring utility and the HYSYS blowdown, right? So just to make it clear that the blowdown is the recommended tools or technology for depressurization, right? It is has been trusted by the industry proven technology, right? It considered the nuclear boiling. It just like I described just now, it considered the rigorous vessels piping orifice model, right? It also the thermodynamic able to handle the dense phase fluid, right? And the other thing, I think, when you use the depressurization utility, you need to put constant, like for example, the PV work term, the recycle efficiency, right? Sometimes this is a guesswork, right? So with blowdown, you don't need to input type of constant, right? So this no longer kind of guessing what parameters or PV work terms I need to use, right? So yeah, it also is built the with the better user interface, right? You can see later on, like the tab is based on the workflow, right? No hidden parameters to toggle to remember. Improve graph, right? We're no longer using a strip chart, but we have a data captured automatically with the plot, right? And also a report comprehensive result summary. Okay. In terms of the calculations involved in blowdown, right? So what actually all the calculation involved? First, of course, the fluid mechanics, right? It could be one dimensional, one phase, or multi-phase. Three-phase is also possible with highly water content, right? Also, of course, the thermodynamics, right? So the multi-phase, multi-component, near critical, right? We actually have to predict the phase envelope correctly or right accurately, right? The liquid density, the latent heat, right? And also the mass, the heat and mass transfer, right? So the heat transfer from the environment, the fire case, right? The conduction, convections, then boiling, and also the radiations if there is a fire. Okay. Right. So, okay, in terms of just to discuss on the thermodynamic model is use the proprietary equation states of model. It's only available in blowdown, cannot be selected in property environments. Sorry. It has a set of component lists, a standard set of component lists, right? It is the property environment of the equations of state is superior in predicting the supercritical fluid properties, right? And it's fully rigorous and predictive. No need to specify again the PV work or the recycle efficiency, right? So this is to just to give illustrations that uh, in the upstream applications, right, the conditions of the vessels is actually start at the supercritical region, then it will move across to the vapor liquid envelope, right? And blowdown can predict this kind of change of the trajectory, including the change of the properties accurately, right? So if we are not able to predict this kind of the thermodynamic calculations of this, then we will result in maybe could be oversized or undersized, right? Depending on the case. A poor result. Okay. Right. In terms of the orifice calculations, these are kind of the background, the details. The expansion is assumed to be reversible from upstream to orifice. Then it's assumed irreversible from orifice to the downstream, right? Uh, the pressure drop in the piping of upstream is neglected, right? The shape of the orifice itself is typically is reflected in the discharge coefficient you're using, right? So for uh, what is discharge coefficient actually is a ratio between the uh, actual, right? What can pass through that orifice or opening, and basically to what theoretically can actually the maximum can pass through that opening, right? So it's like an efficiency of the opening, right? So typically it's about zero point 0.9 for gas or a mix of gas liquid, right? Assuming homogeneous equilibrium model, right? And about zero point 0.6 for liquid or flashing liquid. Okay. All right. So this is the snapshot on how you use the blowdown system, right? Okay. So basically, let me also show this in the home, right? You have this safety study, right? When you click this, right? So you can see here there's a blowdown depressuring. So you can just click blowdown and it will open a form like this. You can name the form, right? And you choose the 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 form here. Let's sorry, the template, for example, a single vessel template, right? Okay, there are several template available, right? Then you can click start analysis. Okay, so this also uh, to give the calculation basis, right? So the vapor is actually pressure driven, right? So vapor is you can flow the vapor can flow upward, right? But for liquid is actually gravity driven, right? So it cannot flow upwards, right? So whatever if there is any multi-phase, right, it will drain to the logical place, right? If, let's say if there is any multi-phase here, the liquid will drain, right? So this is also taken into account, right? The liquid drainage, right? That's important also to predict, to accurately predict the wall temperature, right? Because the liquid will actually act as moderators and will result a milder temperature predictions. And okay, so typically blowdown is performed in two types, right? The cold case, right? So assuming that there's no heat input from the surrounding, right? Fully adiabatic. This is basically typically is done to check uh, any issues with low temperatures, right? If there is any potential issues with low temperatures, right? But we also do the blowdown calculation for what is required for fire case, right? So whether we can actually evacuate the inventory, size the orifice properly, and evacuate, confirm that we can reach, let's say, the half of the design pressure within 15 minutes, right? So for fire case, you can apply the duty, the heat input to the volume of liquid, the wetted area, or the entire vessels, right? Okay, I just want to give also by when we are doing blowdown calculations, when we're doing equipment sizing or any sizing, right? Typically, we deal with two types of calculation mode, right? First is design mode, and second is rating, right? So by default, the calculations in blowdown is a rating mode where you actually specify the opening, right? You specify the opening and you check the performance, like whether whether the pressure, uh, the targeted pressure can be reached or not, right? So you put the opening, you check the performance, right? By default, that is the calculation mode of blowdown. But for and this is maybe applicable for existing facility, right? You might want to validate existing facility performance, yes. But for greenfield or designing a new facility, you'll need to calculate the orifice, right? So typically, what we do is we put a adjust, right? So we adjust the orifice opening to target the final pressure, right? And you have to activate this tick to automatically run blow down on input. So what this adjust will do, it will actually vary the opening until it get the final pressure uh, within the time targeted, right? Okay. So let me see. Let me open up one example here also, just to show you what. Okay. So here you can see this is the design. So you put design adjust operations, and basically we target the orifice of the blowdown utility, and the target variable is the final pressure. We can input the final pressure here. Just make sure also the blowdown utility to take this round blowdown on input G, right? So then it will iterate to find the opening, right? So it will iterate to find the opening of the restriction orifice, right? So it will adjust this opening. Okay, right. Just to also, so when we're talking of this blowdown, right? Individual system blowdown, um, especially maybe for existing facility, add additional system, right? That when you calculate the additional blowdown peak flow rate when you add to your current blowdown total blowdown peak flow rate, right? It might actually exceed your flare capacity, right? So in that case, you can see here your flares capacity header or tip might be designed for certain flow rate, right? It will be designed for certain flow rate. So in that case, many companies have considered to actually stagger the blowdown. Means that they will prioritize opening the critical system, but then also some of the system they will not open all at time zero. They will open it at different time, right? Just to avoid the peak, especially for the time zero, to exceed the uh, flare design capacity, right? So this analysis can actually be done easily in the staggered blowdown, right? So you can see here we have the staggered blowdown utility. Let me open also just quickly. Right. So by doing when you're doing the staggered blowdown, you have to do individual blowdown first, right? So basically, it will actually superimpose the calculation from each of the system. Here, you only need to put the flare capacity, right? If you put design, then it will calculate when is the system needs to be open, right? Is it zero or some other time? Right? If your rating is basically you put the time you own, right? So that's just a quick introductions on the staggered blowdown, just in case, right? Right. So this is, I think I've gone through this, right? Then defining the blowdown. Okay, let me open the. All right. So let's say I'm just opening. Right. So actually here, right, you can see. I'll go through this quite quickly, right? The slide that actually explain, right? Give me 1 second. Right. So let me open this, right? So basically here, right, you can see here, um, this is when we define the blowdown, right? So we define where how is the uh, how is the inlet lines, etc. Right? You can see the. All right. Yep, like that. Okay, you can see here. Actually, we can vary. This is typically like, for example, if we put if you want to more, this is, you can see we're removing all the pipe, but you can include, like, for example, like that, the pipe, right? So typically the number of pipe there is depending, like, for example, if your inlet line have vertical, horizontal, then also maybe your line have multiple size, then you can put different segment, right? So we can accommodate up to 5, right? So this is kind of defining the system, right? And again, this is we will define the compositions. We can copy the compositions from the inlet stream, right? Then also the vessels, we define uh, the dimensions, the thickness, the design temperatures, right? And also the orifice, right? Once we define the systems, basically we'll go to the mapping, right? So blowdown will actually look at your component and map. One thing is it will not map the hypothetical, right? So we will need to make decisions on, for example, if your fluid involve hypothetical, how we're going to map, right? So this one I've gone through. Okay, I think this is template. Yep. So if you have vessels, you can system, you can define using this tick box which part is actually exposed to fire, right? Okay. Yeah, so this is the few step you can go through, like copying the initial conditions, right? The vessel definitions, okay, the fire case. Okay, typically we also define what is the initial liquid flow rate. Liquid inventory in the vessels, right? Okay, so here is when we define where we define the individual pipes. Remember, in blowdown we define all the details, right, of the individual pipes. Not we don't lump it together with the vessels, right? So you can see we can put the the material, the pipe schedule, the size, right, the length, if there's any change in elevations, and as well as the design temperature, right? Okay. When you put the design temperature, it will then highlight if this design temperature is exceeded, right, or is violated. Okay. Here is where you put the orifice, right? Remember, by default is a rating calculation, so you define the diameters and you check the performance. Okay. Touching on the component mapping, I think you can. I guess the time is quite limited, and in essence, blowdown will do the auto mapping, right? But it will not map the hypothetical, right? So we will have to make the decisions. Like for example, of course, the simple kind of the straightforward, the pure, it will be mapped automatically, right? You can click this edit map to view, right? So you can see here certain like for example the hypo component, right? There's a method on how we actually can map to which component, right, based on molecular weights, etc., right? So the details of the kind of the approach is put, I've put it in the appendix of this presentation. Yeah, so this is an example of that, right? So for example, we have to find the component with the closest normal boiling point, right? For example, the N-heptane is the lower molecular list, the N-heptane is the higher molecular in the list, right? And basically, we distribute the components for that hypo into these two blowdown component, right? So this is the kind of the prorating of the the two components, right? So we can see from one hypo component, we split it into this pentane and heptane. Okay, then finally the run control, right? So this is determining when is we're going to stop. So either by time, say 15 minutes, or when the final pressure, the targeted pressure is achieved, right? So once we run, we can get uh, the plot, the summary of findings, right? For example, how much flow is actually passing through the orifice. What about the temperature on different sections on the vessels on the different lines, right? All right. So I think that's a lot. Uh, but I hope that gives a good overview on uh, the the functionality of the blowdown. I think next I will hand it over to Viresh. I'm sorry, I think I've overrun, but let's get to the exciting part, right, of the case study. Viresh, maybe you can share your. You want me to flip the slide, or let me flip the slide? Can you
Uh,
see my screen, Viresh, or you
yes,
want to share?
yes, I can see. And you please do me the favors to flipping it. And
All right.
thank you, Fauzi. Especially, I want to thank you for inviting me to host with you. I get this opportunity to share some of this stuff to the people. Okay. Okay. I have seen some questions. Um, I'll try to capture some of the answers here. Okay. Um, Fauzi has already taken some descriptions about some basic fundamentals and some basic procedures. which I will pass through in a fast mode. Uh, but remember one thing, now since today we are focusing only on how to utilize the utility from HYSYS. We are not talking about technical. There's a lot of other issues related with technical, which is not possible to capture now. Probably we'll have to plan that webinar separately. But some relevant aspects I will still highlight during the course of detailing. So we'll talk about first some description of the system which we'll consider for our cases, right? And then little bit of touching on why we have to do it. Some information about heat fluxes, very high level information about heat fluxes, their role, and when we are using the equations, so-called Stephen-Bowles equation in blowdown utility, what are those parameters? The legacy method, depreciation utility, let me call it DU, and the new method, the analytical method, let me call it BDU, right? And then we talk about the case studies. Next, please. So the cases which we will go through is, first we will size the orifice for a system, which I'll describe you later, right? And use the same old concept of 7 bar G in 15 minutes depressizing, right? Then whatever orifice size we get from this depressing utility, we now use blowdown utility with using the same conditions, but using depressing utility, using the fundamentals of BTU, blowdown utility, and see what is the difference between when we use DU and what is the difference when we use BDU. So once this is done, right, then we will incorporate the concept of heat fluxes, and then see when we use heat fluxes, what does it mean, how does it affect it. So all these three cases will be based on the pool fire. The next two cases, case 4 and case 5, we will talk about jet fire, and how the same orifice size, when it is jet fire, what happens. And then we'll try to figure out whether it was good enough or our equipment is rupturing. If it ruptures, then what should have been the orifice size. So that is how we'll cover one single case in different cases, one single system in different scenarios. Yeah, next please. Yeah. So on the left hand side, you see this is typical system which you will experience on your facilities. Separator, you have got inlet, you have got liquid outlet, you have vapor outlet, vaporator, or some branches, right? Normally, it is very good idea to convert this information into tabulated data, where you write about different piping, different thicknesses they have, different length, because all this information will eventually get converted into volumes, and this different materials will contribute in differently, right? And then the operating conditions of the system. For our case, we have taken hydrocarbon liquid and vapor. Normal operating pressure is 10.5 bar and 60 degrees centigrade. But often when we do these type of studies, client will ask you to keep your initial pressure at pressure high, because they want to be conservative, right? Though during blowdown facilities, whenever blowdown takes place, normally it is operating at, like for example, 10.5. But then for the conservative point of view, some companies would like to consider as a high. So let us say before the blowdown starts, the pressure will be 14 bar and corresponding temperature. In this case, the liquid is 1.2 meter, right, from the bottom. So next slide, please. So that was the system. Now let us see about the heat fluxes. So you can see one vessel here, this sphere, right? Below this sphere is a pool fire. The pool fire has spread out in such a way that there are some areas which are in touch with the fire, and some areas means surface area of the equipment, they are not in touch with the fire, but they do absorb the heat, right? So the one which is directly in touch with the fire, you can call it as a local peak heat load. The heat load due to local peak, right? Because they are localized. But then the rest of the area can be taken as global average heat load, right? It is averaged out. But important thing here is to understand that it is the global average heat which is the main cause of the rise in pressure inside. But then local peak heat is the one which is responsible for increasing the metal temperature. The surface area exposed to local peak heat is less. So it hardly contributes into increasing the pressure in the vessel, right? So these 2 points are important. So this is for pool fire, right? So for pool fire, as you can see, local peak heat occupies more surface area. Now let us go to the next slide, please. In the next slide is jet fire. So jet fire is something which is coming from the source, the leak, right? So the local peak heat load occupied heating the vessel, the surface area is quite less as compared to pool fire, right? But the intensity may be more, right? But then fundamentally the same thing. The rest of the area which is not experiencing the heat directly, the heat absorbed is called global average heat load, and that is the one which is responsible for increasing the pressure inside. Next, please. Now, since blowdown utility is analytical study, right? So the equation at the top, which you see here, it is using the sigma Q absorbed is equal to sigma. That sigma is a stable Boltzmann constant. So the first portion is heat absorbed due to radiation plus heat absorbed by convection. Of course, convection is there, which is not shown here, which was always there. So this is the main equation, and this is the equation which is solved by blowdown utility. And the parameters which is given on this table are the parameters which we need to know to input in the utility, right? So ultimately, what is our objective? Our objective is to find T surface. All the other parameters will be available. I'll cover in the next slide, right? But our ultimate objective is to find out that what is that surface of the, what is the temperature of the surface as fire is proceeding and temperature rising. So that is our objective. Actually, by mistake, the circle is T gas. It should be T surface, not T gas. Yeah. So because we are trying to find out the surface of the temperature of the surface. Okay. Now there's a mention about table A2 and table A3. In API 521, there are two tables for pool fire. There are two tables for jet fire. So those two tables, we are not going into detailed part of that, right? But then there are two tables, and we are supposed to take a decision which one is relevant for us. I think there is a need to have a separate webinar where we talk only about the technical part of it. But at least in this webinar, you just understand that how we can use the utility and achieve the objectives. But what information you have to feed into that utility, probably we can discuss in detail later, because we don't have enough time to capture everything. Next, please. Next, please. So now the previous one, yeah. So if you see here, this table is for the pool fire. So I said there are two tables for pool fire. This is one of the tables, right? So all this information which I said we have to enter in the utility, right? So that data is available here. So if you can see, the first column is surface average heat flux. Second column is local peak heat flux, right? Because local peak heat flux is the one which is responsible for rise in the metal temperature. Surface average heat flux is the one which is responsible for increasing the pressure, right? So that information available here, right? So this is for pool fire. If you notice here, pool fire, again go back please. If you see in pool fire, your heat absorbed, the last row is 45 kilowatt per square meter, though peak is 120. Now let us see jet fire, the next one. So in the jet fire, if you see here, it is 85 or 290, depending upon which scenario we're talking about, right? So same type of data, but this is for jet fire. Now surface average heat flux and local heat flux, this has got other two components. So more than 2 kg per second and less than 2 kg per second. So this is another aspect which we need to understand. I'm not going to detail at this point of time, but then to give you some idea, that these two different flow rates are meant to give you flexibility to take a decision. See what happens in the jet fire. In the jet fire, when the jet fire starts, the power in the jet fire is enough because pressure is still there, right? As draining will take place, the pressure inside the source will keep on decreasing, right? So the length of the jet fire and the location where it is hitting will keep on changing, right? So slowly the fluid coming out of the hole which is causing the jet fire will keep on reducing. So that is our two flow rate. So we are supposed to handle these two flow rates. How we will handle and how we do it, we will not be able to capture now. Next slide, please. Okay. So now we will start working directly for using that example, right? So this was our system. So if you were using depressing utilities, you see the total volume which you get here. This is what you are normally entering depressing utility, right? So everything lumped into one is shown here, right? So the next one is number two. Number two is diameter, right? So you can decide the diameter and then it automatically calculate the length based on the total value which you entered. Then number three I mentioned is the metal. So this because you are supposed to enter here how much portion is in contact with the liquid, right? Because in your real life your liquid is only in the liquid leg and the vessel, right? But here you have combined everything into one vessel, right? So be careful about that liquid here is properly entered here, right? Because the percentage of liquid in V101 and the percentage of liquid in the lumped vessel probably is not the same, right? So that care is required. So anyway, this is something which you already had been doing and you already know. Nothing new about it. Next, please. So Fauzi has already explained you all this thing, right? So if you want to find out the calculated area, this is how you enter the initial pressures, final pressures, and durations, and you get. So in this example, which we have taken for demonstration purpose, the RFA size we are getting is 26.31, right? So all this Fauzi has already explained. I move to the next slide. Now here. Now the same system, now we want to talk in terms of blowdown utility, right? You see, so you have got a vessel here. You can represent all these pipings into different configurations, right? Like you want to have at the your blowdown is at the inlet or at the vapor outlet, whatever, right? But important thing is here this. I have given you a very simplified version of the system. But whatever system you will be dealing with, now here you have to figure out that out of this whole system you are considering which part is going to be exposed to global heat flux, which part will be exposed to local heat flux, and how much, which of the piping will be exposed to what type of heat flux, what type of heat, right? So to get all these answers, I'm sorry, I'm afraid this is not the right place, because it is a whole lot of other detailed part of it. So I will not be able to do that. But important thing is this, that here you have the opportunity to decide that which section of your system is going to be exposed to what. Like there are some systems which may extend from a source to some other location, and in between there is a bridge, or in between there is a firewall, or in where there is some structure, right? So that means the heat may not be able to go that far, right? So to be able to do justice properly with the component and giving them proper heat absorption is a very good idea to have a very good knowledge about 3D model. And those people who have been on the site, they are the best people, because visualization is very important here. Without visualization, without having the understanding how the pipes are routed, in which direction, which of the pipe of this system has gone to the some other deck or has gone to the lower deck, whether that will be exposed to fire or not, right? So plays very important role. Next slide, please. So when you will be entering that information, right? So this is the sequence of information you will be entering: 1, 2, 3, 4, 5, right? First you enter the design data, then system mapping and all those things, right? Like that. Let us see if we can give you some indication about the example we have taken and how we have entered the data. Next, please. Now see here, uh, this vessel has got inlet, vapor, liquid, blowdown, tailpipe, right? Right. So what I have done is to represent my system, which is on the right hand bottom line. So I thought that this type of configuration which you see here, inlet line, how many vapor diode around, right? So I tried to find out uh, how many numbers of which type of lines can be representative here, right? Each of the type can be 0 to 5. So almost 35, 40 pipings can be accommodated. But suppose your system is too big, right? And you want to lump. So when you want to lump, like for example, the piping just above the vessel vapor outlet, right? The first and second, right? Suppose suppose there are something which you have to lump, right? And suppose you not possible to accommodate into the whole system, right? So whenever you want to lump, make sure the lumped pipe have a same thickness. It should not so happen that you have lumped the piping to make the common volume, right? And different thicknesses, because different thicknesses will absorb heat in different way, right? So make sure that when you lump it, the thicknesses should be same. Okay, next please. Now this is about the when you start entering the data in the system template parameters. So in the template parameters, what you are doing is you are defining your air temperatures, because your air speed and air temperature is going to affect the heat carried away by the air, and ambient temperature will affect the heat absorbed by the vessel, right? So you enter that data. Then initial conditions, like I said, some companies want to start their blowdown based on your pressure alarm high, right? Or 90% or 85% of the safety valve setting, or whatever your company decides. Or if you are from consultancy background, whatever you have been advised to do. If there are no instructions from my side and you have the liberty to take a decision, so probably you want to be conservative, right? Now at the bottom right hand, where you see in fire zones, right? So there are different piping on the left hand side, unit operations, then type, right? So you have got a vessel and so many pipings. So this is here where you decide whether it is a pool fire or it is a jet fire or it is a heat flux, global heat flux, or it is a peak heat flux, local peak heat flux, whatever it is, you select here which one you want to be exposed and which one will not be exposed, right? So this decision, which pipe will be exposed or which will not be exposed, is your decision, and you will decide based on your own experience. Your experience will be based on what you have seen, how much you understand about the layout, and how much you understand about the piping routing, and how you understand how the system has expanded from one area to another area, right? Which means PNID alone will not be able to help you. In PNID, you will not be able to get the idea that how your system is going to be extending from one area to another area, or one deck to another deck, right? And how the fire is going to affect those components, right? Okay, next slide please. So this one, we are talking about the stream, right? Because if it is a simulation, so you need to have stream to be defined, right? So that stream you can link, because blowdown utility is going to be a standalone separate simulation model. So what you can do, you will have some main model for the whole facilities, right? So from that model, for every system which you want to deal with, there will be some inlet stream, right? So in that inlet stream you can export and then import back to the new slide. Right? So then you can link it. but make sure that stream that stream is well defined, means it is already solved and not unsolved. Correct. So if you see here, this is composition, right? PAS1, PS2, PS all pseudo components. Correct. I will talk more about this. Okay. Another thing, if you see here, H2 is 0, H2 is 0. So global feed at the top, above base is 1, at the top, global free water phase. So if your system, still further up, yeah, this one. If your system has got water, which will be separated, and it is something like 3 phase, right? Then you have to select this one, right? You have to select this one. And when you mention about the initial conditions, there you have to mention how much water. Okay. Otherwise the water will not be captured. So you have to select that part. Okay. So let us go to the next slide. In the next slide, you talk about the internals. So your vessels will have some internals or will not have, right? And if you have, then mention internals. And then you are supposed to mention that zone specified a uniform distribution. The idea is that heat absorbed by the internals has to be accordingly captured, right? But if you do not, if you say none, it is like a conservative. That means you want all the heat to be absorbed by the vessel itself, right? So you can mention, you can select none also. It will be a bit conservative. So there is no harm in if selecting none, though there are internals, but you can still select none. But the only difference is it will be conservative. Next, please. Now I have been talking about heat transfer, right? So we already have entered the data, mechanical data, right? Now we want to take a decision whether the type of heat which type of heat we want that component to absorb, right? So you have the option to select whether it is simple or it is Stephen Boltzmann type. Simple means same type which you normally do through DU. Stephen Boltzmann means the type which you will do through BDU, Blowdown reality. Correct? If you see here, the information for simple fire is mostly automatically updated. Automatically it is populated. You don't have to do much thing. But for stepper Boltzmann fire, you have to manually enter the data, right? So in this case, for your example, I have taken jet fire, right? So this information has come from where? Let us see. Can you click that back arrow at the top? Yeah, this one. So you see a jet fire. So local peak heat flux and then surface average heat flux, right? So if you see here the temperature 900, and your heat absorbed 85 and your heat transfer coefficient is 40. So that information has gone there. But I have taken for only more than 2 kg. Like I said, this is a bit detailed part to explain to you. More than 2, less than 2, all those things. Unable to capture now. Okay, let us go back to the same slide now. Okay, so all this information is coming from there. So that is how those tables are used. So let us go to the next slide. In the next slide, again, you are mentioning initial conditions. Initial conditions, no, still go back, the initial condition here. Now, if you see here we are mentioning how much is the liquid, 1.2, right? You can mention percentage also, anything. But suppose you had selected water also, right? So there will be 2 more or 3 more rows to account for the water also, right? Okay, next, please. Yeah. So like that, just now we discussed about the vessel. So similar information we have to do for piping also. Everything same, almost same, right? So which we are not doing it because it is exactly the same. The only thing is instead of vessel, it is a piping. Okay, next. Then here we are entering the orifice size, as we said earlier, that whatever orifice size we have calculated for first case, we'll continue to use same one. Discharge coefficient. Okay, discharge coefficient will depend upon whether you are using relief valve or you are using suction orifice or you are using control valve, where all these will have different discharge coefficient. I think somebody had put the question whether discharge coefficient is as per Shell standard or something, right? No, that is you have to decide. HYSYS will not decide. HYSYS has got default value as 0.9. It is a default value, but you have to decide whether you want to use Shell or ISA or anything or from the vendor. It is up to you what you want to decide. But then be careful about the default value, because default value is 0.9, which is more close to the relief valve. And then view under here opening timing. Okay. So if you see here the bottom portion under the view, right? It is a open timing and open diameter. If I want to blow down in such a way that for first 10 seconds, I do not want to open the blowdown valve. After 10 seconds only, I want to open. Why? Because I want to do stagger blowdown. I want to give priority during those 10 seconds to some other system as a stagger blowdown. So in that case, what do you do? Up to 10 seconds, you keep the diameter 0. After 10 seconds, you enter this diameter 26.31. That means next row will be time 10 seconds and diameter 26.31, and first row will be time 0 and diameter 0. Right? But then if you write diameter 0, calculation may not take place. Right? So write 10 to the power minus 3, minus 4, minus 4, some number, negligible number. Right? Okay. This is some sort of cheating the simulation. Okay, next, then back pressure. That back pressure is the one which you want your system to experience. When you blow down to flare header, right? Or when, typically flare header. So flare header, keep that pressure at 0. It may be 0.5, right? Because these pressures are only important when it is when it is not a choke flow, right? It is subcritical flow. But anyway, your main concern is in the beginning, not toward the end. You are more concerned about the initial part where you want to find out what is the peak heat, peak blowdown rate. If you put higher pressure, then probably it will stop at that pressure after depressurizing. Okay, next please. So this is same thing. Okay. If you see here on the left hand side pseudo component, this is mapping, and how pseudo components have been converted into. I think there were some questions. Somebody has asked why only 15, not more than 15 components can be accommodated. Yeah, your stream may be having 30 components, 40 components, right? But then for HYSYS, it will convert it into, even the pseudo components are converted to equivalent. Like for example, you have C6 plus, right? So everything is lumped into one, right? Similarly, it will also convert into relevant equivalent components, right? The idea here is this, that your main concern is not the very heaviest. Your main concern is that part of the liquid which will get vaporized on absorbing that heat, right? Okay. So what is the next slide? Next slide, please. So in the next slide, hold condition, I mentioned 1800 seconds or 7 bar, right? It has no meaning. The only thing is you want to make sure you are able to run as long as you want. This sentence will again revisit when we see the graphs of the cases, right? And there are on the left hand side there are 3 cases. Left hand side means in the center, where it says that time step is 1 minute, 5 minutes, right? So initially, it is good idea to keep the time space very small so that your peak is captured properly. After that, once some of the blowdown has taken place, you can have a longer time span, right? Because in that case, your peak is already captured, so it wouldn't matter. But it is up to you how much sensitivity you want or accuracy you want. Okay, next please. So once you will have run and it is completed, your result will be populated like this. You will have three different specific zones, plots you will get, then major findings, and then orifices. Just let us see what is in the plots. Next slide, please. Next slide, please. So in the plots, you will get plot like this, right? So on that blue color under variable set, you see the overall metal temperature, right? So there's a whole lot of list what you can plot, right? And on this variable, you can select which one you want to be plotted, right? So you can find out the liquid temperature, the vapor inside temperature means the wall temperature in contact with the vapor which is inside or outside, right? Liquid temperature, vapor temperature. There are a lot of other information available, right? And you can select which one you want to be plotted. Once this has been plotted, you see the table at the center. So HYSYS has got a provision to view that information of the plots into the table. In this table, you can get all this tabulated data. And good thing is this tabulated data can be copied and pasted on Excel sheet. Right? And we'll see how we are using that information. Okay, next slide, please. So in the major findings, you will get all those information, what has happened during the simulation. Any constraints, anything which is abnormal, right? Typically, you will find here that at the inlet, the initial inventory which you mentioned was something like 16% liquid, but then in the stream which you have defined, right, it is not 16%, it is 10%, right? So you are basically, when you define 16 and it's actually 10, that means simulation model has to change the composition in such a way so that the liquid formation is increased to that level, right? So don't force. Be careful about the inventory of the liquid when you mention in the initial conditions how much percentage it is. Otherwise, simulation will assume that the initial inventory which you have entered is the correct value, right? And the stream which you have used to input as a composition is to be corrected, right? So simulation will automatically correct it to suit condensation of not condensation, the liquid formation into the vessel to that, right? The liquid is in the vessel, liquid is getting collected, right? But in the stream, it is flowing per hour or per second. But in the vessel, it is accumulated, right? So one thing you can do is based on your stream, you can check the actual volumetric flow rate and accordingly find the percentage to be more relevant and correct. Okay, next slide, please. So orifice results, yeah, Fauzi has already explained you all this. And next. Now I was talking about how this data in the result, the chart, the graph can be converted into table. And in this table, if you see here, like all this blowdown utility, our intention is to find out that what is the metal temperature, what is the temperature of that metal which is experiencing that heat, right? So which you get here, right? And then because we want to find out the rupture will take place or not. So that means we want to find out that the ultimate tensile strength at that temperature, right? So temperature you get from HYSYS, which there's a table here. This table is from API 521, right? And since we are given two references in the beginning, so the same table is available in second reference also, which is scan power report, right? But the API has got a bit different data than the scan power report because the sources are different, right? but it's up to you or your company to take a decision whether you want to use API data or you want to use snap property report, that scan power report. I prefer to use API data, right? So based on these metal temperatures, you are able to find out what your tensile strength, right? So once this information is available to you, you can convert this data into your Excel sheet, right? So you copy the metal temperature to your Excel sheet, you have got time, right? And then you can find out the von Mises stress. Von Mises stress is that stress which is inside the piping or in the vessel, which is going to be due to the pressure, increasing pressure, right? So there's a formula. There's a formula in API 521. There's a formula in that report also, scan power report, right? So these two things are you can put in your Excel sheet. You can have tabulated data and then plot also, right? And then you can some sort of write here that whenever tensile strength, whenever stress inside is more than the tensile strength, it will rupture, right? So if stress exceeding the tensile strength, it means rupture, right? So that is the meaning here. So it is possible to get the data, but from HYSYS you get the temperature first. The rest of the things you can do through Excel sheets. Okay, next slide, please. So we will have 3 examples for pool fire, then we'll have 2 examples for jet fire, right? So for pool fire, we do simple one. We will give the result for simple case. Then the same again same one. Now here for the second one, because we are using blowdown utility and we have that option of selecting the heat fluxes. So first we will do only global average heat flux. Why? Because so far we had been using only depressing utility where we never talk about these fluxes, right? So let us see when we had not bothered about these fluxes, what we get, right? In the third example, we talk about average heat flux as well as local heat flux. Remember, I told you local heat flux is the one which is responsible to increase the metal temperature, right? That was about the pool fire. Now jet fire. Now jet fire has got different heat fluxes and different heat transfer coefficients as compared to pool fire, right? So naturally the result will be different. So for jet fire, so whatever we have done pool fire, we check using the jet fire now, and then see whether there is a survivability or not, right? So now let us go through the cases. Next, please. Now this is case 1. So no need to talk about theoretical, just see the results, right? So this is the equation people had been using for this depressing utility, right? And the outcome is that you are getting orifice 26.31, right? Calculated one. Now pay attention on that equation. This equation is Q, kilowatt, 43.2. F is typically that factor 1, which is meant for whether you got sprinkler or not, drainage or not, right? Then area to the power 0.82. Assume your area is 1. Suppose I want to call it flux. That means I want to call it kilowatt per square meter. So Q by area. If everything is 1, then it becomes 43.2. 43.2 kilowatt per square meter. Actually, not per square meter because it is not actually not squared. It is 1.64. But for the sake of comparison, we'll say it is 43.2 kilowatt per square meter. Next, please. So that was DU, difference utility. Now we are using blowdown utility. Blowdown utility, where now we are using the global average heat flux. You remember I gave you how to enter global average heat flux. What are those data? Those tabulated data, right? Now same system, same orifice size, but using global average heat flux, which is different value, right? What you get here is you are getting depressizing and in 15 minutes to 9.4 bar. Earlier it was 7 bar. Your temperature earlier was something like 73, 74, but now your temperature is 350 degrees centigrade. And still we have not talked about the local peak heat flux. We are talking only about the global average heat flux, right? Probably this change is because for the heat absorption, heat flux is 45 kilowatt per square meter, while for DU it was 43.2. So there is a extra heat flux. The extra heat flux, that is why it is taking longer time and higher temperature. And one more thing which I want to say to you is that when depreciating utility was being used, right? Uh, I think, is it possible to go back to earlier slide where we have taken the extract from API 521? I have put some red color highlighting. I think slide number 9 or 10. Okay.
Yes, Virash,
Now, if
please.
you see here, the red color, it says depressurize the exposed equipment such that the reduced internal pressure keeps the stresses below the rupture stress or until the acceptance criteria for rupture are reached. It was always mentioned there like that, correct? It was always mentioned, but in the next section, they had given this idea also that if you can depressurize to 50% or 7 bar G in 15 minutes, um, you are able to to achieve the objectives, right? Which was meant basically for 25.4 mm thick carbon steel, right? And it was meant for pool fire only, right? But then at that point of time, they had mentioned that you should do more specific calculations or use some simulation, right? But at that point of time, not enough data was available for heat transfer coefficients and heat fluxes, right? At later stage, there were two tests carried out, BRL and BAM. BRL means some ballistic research lab, and BAM, something like material research and testing. So these two tests were carried out, and they were able to get very useful data. Those tables which I mentioned earlier, that two tables for pool fire, two tables for jet fire, they are the one, right? So that is why once those data are available, people started coming up with the softwares, and that is the result of blood utility you have here. Okay, let us. Sorry, Fauzi, can we back? Can we again go back to those cases? I think case number 2. So by saying all these things, I'm saying that now you have got more reliable and more representative data, which means you should prefer blowdown utility as compared to depressing utility, right? So somebody had put some questions that which is the correct method, I suppose, something like that, right? So it's not question of correct method. Question is, what do you want? By saying that you are able to depressurize to 7 bar, do you think you are safe? Have you been able to avoid the rupture? That is the question you should ask. But then by using depressing utility, you don't have that answer. You only have the answer that you have succeeded in depressurizing the system to 7 bars in 50 minutes. But it doesn't give you the indication whether it will rupture or not. And at the same time, that is also not defined what type of fire you had, what heat flux you had. It's all black area. Okay, number 2. So this is what I was talking about. So I already told you that how by using correct heat fluxes, you are getting this information. Abdul Wahab has posted something. I would suggest now at this point of time, you focus what I'm talking about, right? Digest it, and later you can have a lot of questions. You can keep posting the question. You can directly keep on sending to us. Maybe in next webinar we try to capture all those questions. But at the moment, we try to focus. I'm trying to highlight to you that when you using depressing utility, your input is very limited. You are not able to take a lot of decisions. So whatever utility, whatever DU asks, you just enter data. It doesn't meet your all the requirements. In Brown utility, you have the freedom to take a decision which system will be exposed to what file. That is a different thing. That earlier during depressing utility, you didn't have to know more. Since you didn't have, you are not required to enter more data. That is why the results were for different order, right? You are not able to take a decision whether it will rupture or not. So anyway, let us go to case 3. Case 3. Now here, what I have done, I have introduced local peak heat flux for the pool fire, right? So which means when I say local peak heat flux, that means I am trying to say that this system now is exposed to pool fire and some portion of the system is exposed to local peak heat flux, which means that wall will start getting heated up now. If wall is getting heated up, that means tensile strength is also going down. So that is why on the left hand chart you will see red color is the temperature increasing, the blue color is the tensile strength decreasing, right? And at the bottom is the stress. So this stress is resultant of two phenomena. On one side, you are removing the inventory, means depressurizing. On the other hand, the fire is increasing the pressure by heating the gas, or if there's a liquid, vaporizing it, right? So this is a dynamic phenomena. So anyway, in this example, which I had taken as orifice size 26.31, right? Same orifice size as we started with the depressurizing utility, and you find that this is very close to each other. After 25 minutes only, you get this. Yes, I was trying to say, how long you want to depressurize depends at what stage you get the confidence that it will not rupture. It's not question of 10 minutes. It's not question of 15 minutes. It's question of at what point of time you will get that confidence that yes, it will not rupture. Right. So here we see at 25 minutes, it is almost parallel. Most probably it will not rupture. Even if it ruptures, it will have a very low pressure. Right. Remember, I talked about how much, what are those conditions where rupture is acceptable. Now, since we are focusing on the utility, we are not talking much on the technical part. That is why I'm not going into detail of that part, right? So what I'm saying here is, same orifice size, wall temperature has become 780 degrees centigrade due to peak heat flux. System takes 25 minutes. Should there be a significant, okay, assume there is a tensile strength and this stress, there is a lot of gap, right? You can decrease the orifice size to bring it closer, but not cross. The idea is, why unnecessary to blow down extra gas when it is possible to manage with the smaller orifice? Okay, next one. Next, please. Now, case 4. Now, that was pool fire, right? Now it's jet fire. Before I talk about jet fire, I want to mention this question to you. How do we know I'll experience only pool fire and not jet fire? Will I get jet fire or not? Who will decide that? Are my facilities such where only pool fire is possible? Right. I'm not answering those questions here. But I'm forward. I'm giving question to you to think, right? So whenever we capture the next year webinar, then we'll go into detail of that part, right? I'm putting all these questions for you to start thinking that more I know about my facilities, better justice I can do, and there are tools to get the answers, relevant answers, and take some nice decision. Orifice size same, right? So here, if you see here, the moment I start assuming that is a jet fire, right? The vessel ruptures. If it is pool fire, it doesn't rupture. If it is jet fire, it ruptures within 5.5 minutes, right? How can I guarantee there will not be jet fire? Can I guarantee? If you can guarantee, if you are sure jet fire is not possible, then pool fire is okay, then probably your orifice size was correct, right? But suppose jet fire takes place and your equipment is exposed to jet fire, this is what will happen, right? So anyway, because this is jet fire, the heat fluxes are very high, and that is why the pressure rise, in spite of that size, has not been able to depressurize to the lower numbers, right? So this is what it is. And then the next case, which is also jet fire. Next case is jet fire. Now here, what I try to do is, though same conditions, but now I am trying to find out that how do I avoid this rupture during jet fire also, right? So I have to increase your FA size to 45 almost double, correct? But then I get that confidence that it has survived. If it is design, if you are designing new facilities, you still have the control on your flare size. If you are designing, if you are rating the existing facilities, your flare is already decided, the size, right? And that is where, after having carried out the studies of all the segments, suppose your facilities have what, some 10 15 segments, right? Out of 10 15 segments, you find out that orifice size of almost 50% have increased. Naturally the blowdown rate also increase, if and most probably your flare handling capacity also increase, right? So that means now you will have to think of staggered blowdown, right? Okay, next slide please. Next slide please. So what I'm trying to say here is that by using these utilities, depressing utility and blowdown utility, what you can do is find the section experiencing the minimum temperature. Okay, there was one question about minimum temperature, right? Somebody was asking about minimum temperature minus carbon steel can take how much, SS can take how much, right? See, by using the cold blowdown, Fauzi has explained to you about the cold blowdown. Cold blowdown means when there is no fire, right? The blowdown is starting from your normal conditions, shutdown conditions where temperatures are close to ambient, right? When you do blowdown at that time, then your temperatures, especially at the tailpipe, will go very low, right? So it is that temperature. So HYSYS will not tell you which material to use. HYSYS will tell you that your temperature can go to this much low, and then you find out to accommodate that temperature what material is suitable to you. It helps you to take a decision which is the right material for you, right? But then you have to use cold blowdown. Okay. Find the section experiencing minimum temperature during depressurizing. Okay, just now we talked. Size the orifice to ensure vessel piping do not rupture during fire. Okay, size orifice to meet rupture criteria if rupture cannot be avoided. Okay, I have not talked about what are those different criteria which are acceptable, because company is supposed to take a decision if at all it ruptures. I cannot avoid the rupture. What do I do? What are those conditions where I can accept that? Okay. The RO, okay, strategize the stagger blowdown. Okay, I already explained to you stagger blowdown, design blowdown to avoid. Okay, operating companies do not like to encourage passive fire protection because of the risk of corrosion under insulation, right? So that risk is there. That is why it is not preferred. So as far as possible, we should try to handle by using the blowdown. And now because of these tools available, the accuracy levels are also very high, right? So it will be very easy and convenient to figure out that which system uh, can be readjusted, staggered, right? If worst come worst, nothing can be done, then of course, then you go for best fire protection. If there is no solution, right? Then of course there are many other assumptions, if right? So like that. So with this, I know I didn't speak a lot about the technical part of it, but I'm sorry about it because that was not the intention. The intention was to only focus on how we can utilize these two utilities to our benefit, right? So with this, there is some question over here. So 0.82. Okay, it's Abdul Wahab had put some question which yeah, what you are saying is right actually. Yeah, what you are saying is right. Yeah, as area will increase, your value will keep on decreasing, because the idea here is to show that that better surface area will keep on decreasing, because that was the intention of the DU, right? But then BDU has got different concept. Here the idea is you already have defined the liquid in the vessel or in the piping, and then you are defining how much is the heat flux, and then the whole of the liquid will experience that heat, absorb the heat, and then start vaporizing based on depending upon its boiling point. Okay, with this I
Right.
finished my work. Fauzi, over to you.
Yes, thanks a lot, Viresh, and I think thanks a lot for those who are staying. I see still a lot of attendees staying. I'm really sorry that we exceeded. I think there's a lot of discussion, and I'm sure we haven't finished. I think some of the question has been answered, but I think since the time we have already exceeded, what I will do, I will discuss with Viresh, and as much as possible, we will try to address it in written formats to the registered email, right? But again, I have disclaimer. I think Viresh should also, right? So I mean, we are doing this. Hopefully, I mean, we're trying to do our best in terms of based on our experience, right? But of course, everybody needs to, or our companies needs to have their own due diligence, etc. Right? Don't don't sue us because of our answer. I'm just putting that right. Okay. All right. I think I would like to maybe I'll end at this, right? You can that's the contact of Viresh and myself, right? You can connect us with in LinkedIn if you have not. Uh, Also, just a brief. This is will be posted and sent later on. You can register for the upcoming technical sharing session. Yeah. All right. Thank you. See you again in the next future session. Right. Thank you. Thank you. Thank you. Thanks a lot, Viresh. Thanks a lot, everybody. You'll get the recording later on.
Thank you, guys. Thank
Thanks,
you very
Viresh.
much.
Yeah.